Now that we know the basic principles of a refrigeration system, let's look at its components. So, I would argue the most important component of our refrigeration system is the refrigerant itself. Early refrigeration systems in automotive capacities and applications were using a chlorofluorocarbon called CFC12, otherwise referred to as R12, meaning refrigerant 12. Um, these were used for a very, very long time and were some of the first and most successful type of refrigerant that was used. And you can see on this the boiling point is well below 0 degrees Fahrenheit. And we've walked away from this type of refrigerant because it caused damage to the ozone layer. The chlorine inside of the refrigerant, also chlorines were inside of lots of propellants for things like hairspray and other spray can like paint and stuff like that applications. So this chlorine would go up into the upper atmosphere and it would combine with an ozone molecule, causing a chemical reaction in which the ozone molecule, which is made primarily of oxygen, it would become unstable, it would lose an oxygen molecule, and at which point now the chlorine no longer wanted to bond with it chemically, and so it would have broken up an ozone molecule, the chlorine would become free, and then go off and connect to another one, and another one, and another one, and another one, so on and so forth, and it depleted the ozone layer. So it was letting in harmful types of radiation from our sun, causing an increase in the global temperature, killing some ice caps and penguins and polar bears and all that kind of stuff. Because of that, we went over to HFC 134A. This has gotten rid of the chlorine, and now it is a hydrofluorocarbon, and it is commonly referred to as R134A. So, this refrigerant has been in vehicles up until 2017 for most domestic vehicles, and this refrigerant has been replaced with a new one called R1234YF, and that has a boiling point of negative 22 degrees Fahrenheit. The reason that we left R134A and went to this new, what's commonly referred to as the new YF refrigerant, is because of the increase in environmental safety that this new refrigerant comes with. When we talk about chemicals that have an impact on the environment like these refrigerants do, they are compared in a format called the global warming potential. And carbon dioxide that we respirate, we breathe that out, has a global warming potential of 1. That's the basis of what all this stuff is based on. R134A has a global warming potential of like 1400 something, so a whole lot more than 1. R1234YF has a global warming potential of 4. And that's why we've moved to it. The systems are pretty similar as far as pressure goes. The components are the same between the two. But the fact that there are hundreds of millions and billions of vehicles out there in the world, and AC has become a pretty standard equipment on most vehicles, and so all these vehicles, as they age, will eventually spring leaks, and the refrigerant from all these vehicles will eventually make it out to the atmosphere. Junkyards are supposed to reclaim this refrigerant, but that's not necessarily done in all cases. Cars, when they crash, if there's a crack in the system, you can't help it. Cars, as they age, and you live in Maine, and so you need their AC, a few weeks out of the year, people just say, oh, it doesn't matter anymore, I'm not going to deal with it. Or every summer they go and get it recharged, but don't fix the slow leak, so the next summer they need to do it again. So you can see why there was a push to keep changing to safer and cleaner refrigerants as we go along, just because there's so many vehicles, and the global warming potential for this stuff is huge. Because then we get away from vehicles and we start thinking about like all the freezers and refrigerators out there in the world running off of refrigerants as well. it becomes a pretty huge thing. The temperatures and pressures of these two refrigerants, R134A and R1234YF, are very similar, and you can see it in the graph that goes on here. And our system, our refrigeration system, is all based off of pressures, temperatures, and then changes of state of matter. So it's nice for the technician that once you learn one system, the other type of refrigerant follows fairly closely in hand, and so you can kind of still rely on your same intuition. Our compressor gets everything going. That's the whole start of this process. So here's what one looks like on the outside. You can see that a belt has a spot for like a V-belt to go on there, or a ribbed belt to go on there, which is multiple V-belts, I guess. So this pulley gets spun all the time by the engine, even when we're not using the AC system. And there's a clutch on the front of the compressor that gets energized by an electromagnet. So when we want it to turn on, a little electromagnet sitting in the center of this pulley gets turned on and pulls this clutch inward. You can kind of see this part right here where the shaft is. So it gets pulled inward and just hits up against the pulley and gets stuck to it, and then starts spinning. And then that spins all this stuff on the inside, and our pistons pump back and forth and create our pressure and flow for the system. There are valves in our compressor, and they're called reed valves, and they're basically just like one-way check valves. When the piston moves downward, there's a reed valve on the inside that's flexy, and so it just gets pulled down and refrigerant's able to pass past it. The piston moves back up. The reed valve has the refrigerant that the piston's displacing push up against the bottom of it. It seals tightly up against the valve plate, and another valve then opens up and allows the refrigerant to go out through another exhaust port. You can see those little valves there, inlet, outlet. That way we don't have to have like a crazy valve train going on. No camshafts or anything here. It's not that big of a deal. And then there's a nice look at the electromagnetic clutch. Just two wires, a big loop of wire, turns it into an electromagnet. We're starting to get pretty comfortable with that concept. And then you can see the friction surface of the pulley, and then our clutch. So this gets energized, it pulls the clutch into the pulley, and this is just the bearing that the pulley's riding on. And this clutch is splined to this drive shaft here, and that's what turns the crankshaft and pistons inside of the compressor. It's actually called a wobble plate, but what you gonna do? We also have these little shims here, and these shims are really important when this compressor gets built, because the shims are what set the distance between the compressor and the clutch and the pulley for the compressor. It's called an air gap because it's a gap that's filled with air. I don't know, rocket science. So if that gap's too great, the electromagnet won't be able to be strong enough to pull the clutch in. If the gap is too close, well, the pulley could end up contacting the clutch and spinning it when we don't want it to be spun. So, or once we engage it, maybe it wouldn't release quite right. Usually with these shims, there's a piece of felt as well, and that felt acts like a tiny little spring. It's just enough squishiness to be able to pull in and then also relax. If we replace a component on our AC system, we always want to drain out the oil that's inside of it. As our refrigerant circulates through the system, it pulls with it a oil. In most cases, it's a PAG oil, polyalkylene glycol. That's why it's called PAG, because that's just what it's made up of. And that oil helps lubricate components. Mostly the components that need lubricating are the compressor, because that's got stuff spinning around inside of it and moving. And then also if we have an expansion valve, the expansion valve needs some lubrication. Everything else is just piping and tubes. So lubricant's not really needed in those devices. But when we get to, like, let's say that we took the condenser out, this big radiator, pull this condenser out, and there's oil inside of it because it got left there when the refrigerant was circulating through. And we need a critical mass of oil to make sure that there's always enough oil in the compressor so that it's always staying lubricated. That's also why they put the compressor down at the bottom of the system, near the bottom of the engine, so that gravity can help pull oil down to it when the system's not running, so that the compressor will be nicely lubricated when we go to start it back up. If we replace a compressor or any other component and don't figure out how much oil is in it, and then add new fresh oil to the system once we're putting everything back together, well, we could starve the compressor for lubricant, just like not having enough oil in an engine is a bad deal, and we could damage the compressor and cause metal debris to go through the system, in which we would need to flush things out, which is time consuming and expensive. If we put in too much oil when we replace a component, then what we can end up having is a liquid getting into the compressor in a high enough volume that we could start to hydrolock the compressor. And that's just, hydrolock just means we're getting some sort of a liquid into a cylinder with a piston in it, and that liquid can't be compressed, and so it would lock things up and more than likely destroy the compressor, especially if it happens over and over and over again. So measuring is always a good idea. Sometimes different service procedures will say, like, when replacing the compressor, add 2 ounces of PAG oil, and that way you don't have to measure it. New compressors, and GM was big on this, new compressors are commonly shipped with a lot of oil in them, and that's just so as they're sitting around they don't build up any kind of rust or corrosion. So a new compressor should be drained of all of its oil, because there have been instances in which a compressor that is completely full of oil gets installed and, calamity ensues. After our compressor, we go up to the condenser, and you can see it's just a big heat exchanger. Our hot vapor is going to come in the top, and as it condenses, it's going to become heavier because it's going from a vapor to a liquid, so it's getting denser. And so our outlet is going to be at the bottom, because that's going to be the most common place for our liquid to accumulate. We're talking 150 to 250 psi going through this, so it's a robust heat exchanger, and we're dropping just a few degrees of temperature. What we're really trying to do is change states of matter, and we're trying to give up a whole bunch of latent heat energy. And where did all that energy come from in the first place? Well, it came from inside the passenger compartment, where we soaked up energy. And some of it came from the compressor that got spun by the engine and got powered by gas or diesel, depending on what we're up to, or I guess electricity nowadays. But we're taking that energy from the inside of the passenger compartment, absorbing it into the refrigerant, and then belching it out the front of the vehicle. And that's what our condenser is helping us do. If we have an expansion valve system, the next component we come to is going to be our receiver dryer, which is this one on the left. If we have a fixed orifice tube, we're going to use a accumulator, which is seen right here. And you can see the receiver dryer pulls our refrigerant from the bottom. Our accumulator pulls a vapor from the top. And the difference between these is expansion valve here, type system on this one. So we go compressor, condenser here, and then to the valve. We want to make sure only liquid goes through our orifice. And then on this one, it's between the evaporator and the compressor. We want to make sure that only vapor is getting into our compressor. Both of these, you can kind of see a little bag right here. This is showing desiccant right here. Both of these, because they're a big enough component, are going to have a desiccant bag in them. And all that is it's like the little flavor packet that comes in beef jerky. It's not really a flavor packet. The little white packet that comes in to make sure that dehydrated meat keeps itself dehydrated. We don't want any extra moisture getting in there. It absorbs it. New sneakers usually come with a bag of desiccant. Sometimes, like electronic components, will have something like that in there as well. And all it is just like a type of salt that wants to absorb any kind of ambient moisture. And that's important inside of an air conditioning system because any water moisture inside the system is likely to freeze at the restriction at our TXV valve or our fixed orifice tube. And because that pinhole in them is so small, that frozen water would plug it up. This desiccant is not there to absorb liquid refrigerant. It only absorbs water, all right? So I know that sometimes when we're talking about states of matter and water at the same time, it can get confusing, but a liquid refrigerant is different than liquid water. Okay. All right, and there's another look at our accumulator there. So you can see from the evaporator, it comes in. If there's anything liquid, it's just going to chill out here until it absorbs enough heat from the engine compartment that it turns into a gas, and then it gets pulled, and off we go. Thermostatic expansion valve. So this is one type of restriction. You can see we have our little sensing bulb, and we have a diaphragm. This is where all the magic really happens. And then we have our actual valve assembly. So the way that this works originally with these styles that have the sensing bulb, which is becoming less and less common on cars, this is just full of the same refrigerant that's inside the system. And this gets taped to the outlet of the evaporator with a very special thermo tape. So the idea is we want to make sure it's insulated up against that tube so that it's really picking up the temperature of the tube and not the temperature of anything around it. So this refrigerant here would change its pressure based off of the temperature of the refrigerant coming out. The hotter the refrigerant, the higher the pressure, the colder, the lower. And it acts against this diaphragm, which then pushes on this spring. If this is too warm, so we're not getting the cooling potential out of our system that we possibly could, well, this increases in temperature and increases in pressure, pushes against the spring, opens the valve up more refrigerant goes in, so with that extra refrigerant we can absorb more heat, and so everything should cool down more. If that happens and we get too cold, well, this temperature reduces and so does the pressure. Temperature and pressure go down, the spring starts to win the battle at this point, and our valve starts to close. It never will close all the way, but it will close a lot, and it will open up a lot too. These systems are much more efficient because the compressor doesn't necessarily need to work as hard. This valve can sit there and change itself around. On a fixed orifice tube system, we have to turn on and off the compressor a whole bunch to make sure that pressures are within this very, very small range, about 20 psi on that low side. That makes it so that our system works properly. So there's our valve open. There's our valve closed. It just works that same way, just based off of temperature and pressure. Modern vehicles have what are called these H valves, and you can see here's my little diaphragm, here's my aluminum block that has the valving inside of it. The difference is there's no sensing bulb that's external. They've actually built the sensing bulb into the valve, so the refrigerant leaving the evaporator has to go past this new sensing bulb, and it still goes the same way. If it's too warm, the pressure up here on the top of the diaphragm increases to the point at which it pushes this valve open more to let more refrigerant enter the system. If it becomes too cold, well, the pressure and the temperature drop up here, and it allows the spring to win the battle, closes this off more, and restricts how much can come in. So that way we're always acting in this like perfect just above 32 degree realm is what we're looking for, so that we don't ice up our evaporator. Superheat. So with refrigerant, we want to make sure that no liquid refrigerant is coming out of our evaporator, and to do that we want to make sure that we heat up the refrigerant to the point where it's a couple degrees above the boiling point, which means that if it's reach those couple degrees above the boiling point, it means everything must have boiled off into a vapor. And so that's the easiest and safest way to calibrate all of these devices to make sure that we protect the system. So superheat just means a sensible temperature above a change of state of matter. So like we could superheat ice and have water that's 35 degrees Fahrenheit, or I could superheat water and have vapor that's 214 degrees Fahrenheit. So it's just making sure we've gained a couple degrees of temperature to make sure that yes, we've definitely changed the state of all of the refrigerant or whatever, but in our case refrigerant. Fixed orifice tube. So it's easy to put these things in backwards, so sometimes we'll have an arrow. My recommendation is just always pay attention to how you removed it, and it'll make it easier to get it back in the right way. And the reason why that's an issue is because it really does sit inside the line itself. We have these O-rings that seal it so that refrigerant can't bypass it. And then our refrigerant's going to go through this tiny orifice, and they put this mesh in front of the orifice to catch any kind of debris. It's not uncommon for the compressor to put a little bit of aluminum into the system, so pulling one of these we might see a couple of flecks on the mesh, which is fine, just a little bit, it's not a big deal. If one of those flecks, however, if it got into this tiny hole, well, that could stop the whole system, and it could cause all kinds of crazy things to happen, all the way to the compressor venting off refrigerant. If we get up around 450 to 500 psi, all the compressors have a little blow-off valve built into them so that they'll just dump some refrigerant out into the atmosphere instead of blowing a line up, or even worse, like blowing an evaporator up inside the dashboard and having a bunch of refrigerant flood the inside of the car. That'd be bad. So they let it go outside instead, even though that's bad for the atmosphere environment. When we find these, there's always going to be a point next to one of these where the line can be disconnected, because that's the only way we're going to get in there and grab the fixed orifice tube. And the way that they code these is by color. So if you pull a blue one out, unless you have some documentation that's saying the white one that you're putting in there is actually the same, you want to make sure you're putting the same color back in there again. They just try to make it easy on us like that. Our evaporator core, another heat exchanger. In this case, we have liquid refrigerant comes in and a gaseous refrigerant leaves as a vapor after it has absorbed all of the latent heat energy from the air, and then also some sensible heat energy too, because it's actually trying to cool the air down. So 70 degree air gets to turn into well, hopefully coming out of our vents, 35 to 40 degree air would be great. We have the lines and hoses, which help the refrigerant get from one component to the next as it travels through our system. They're usually made out of an aluminum if they're a hard line, and if they're a soft line, like usually the lines that go to the compressor and to the condenser, where am I? Condenser right here, will have some rubber soft line to them. Those are going to be multiple layer. They'll have woven metal and then woven mesh and then rubber and rubber and rubber on top of it. But we need that flexibility because the engine's going to torque and move around as we're changing our amount of load that's on that part of our vehicle. Pressure switches, also another very important part of our system. These pressure switches are, one, there's going to be a pressure switch to make sure if our pressure goes too high, the system should turn itself off so that we don't end up having to vent anything to the atmosphere. It doesn't mean that switch couldn't go bad. That's why they still have that last measure, fail-safe. But if our pressure comes up too high, one of the switches should shut the whole thing down. And many vehicles will have another pressure switch in them that will make sure on the low side of the system, if our pressure drops too low, it'll shut the compressor off, because that could mean that we have either not enough refrigerant in the system, we maybe sprung a leak, and so the low side's able to pull the pressure down too far, or we could ice up the evaporator. If our pressure stays too low, that means our temperature on that side of the system is going to stay too low as well, which in our case could cause some ice to happen, which would make it so air can't pass through the evaporator the right way because the ice is blocking up all those little air vent passages through it. And so it would just exacerbate the problem until you've just got like a big block of ice in the dashboard, and the air coming out of the vents is not going to be cold, and it would be something that a customer would definitely have a concern about. When we go and try to get an initial health reading off of a refrigeration system, the easiest thing to do to begin with is to turn the system on and see if it works. If our compressor clutch doesn't engage and starts spinning with the pulley with the engine running, well then we have some sort of a control issue that's causing the system not to run. It could be our refrigerant level's too low, so the pressure switch is seeing that the level's too low. It could also be that the electrical components to control the compressor could be faulty, right? Maybe we have a broken wire, or our HVAC control module, or actually in our case, the powertrain control module tends to control the clutch, so that like if we go wide open throttle, it'll shut the clutch off, so we get that extra like 5 to 10 horsepower out of the engine that the compressor's been using up on us. Also, if the engine's overheating, or if we have a really bad misfire, oftentimes the PCM will say, no, I'm just going to turn that compressor off because I would rather be able to get my passenger to where they're trying to go than keep them cool while they're sitting on the side of the road waiting for a wrecker to show up. So once we have it running, if we see it moving, because we know our components now and the pathway that our refrigerant takes, we should be able to do a touch feel test to see if we can pick up on sensible heat changes as we go along. I never recommend touching the line going from the compressor to the condenser because that's most certainly hot enough to burn you. And it also tends to be down around belts and fans and stuff that's really hard to get to while the engine's running without, potentially putting ourselves in a dangerous circumstance. This line out of the condenser should be nice and warm to the touch, and we wouldn't burn ourselves on that one. So you'd be able to tell if our compressor is really cycling refrigerant and raising the pressure of it, because we'd be able to feel that heat on this line. When we get to the expansion valve, that's usually at right at our crash wall or firewall. So we can't touch this line going into the evaporator, but we can find the line coming out of the evaporator and make sure that it feels cool or cold to the touch going to back to the compressor. And if we had an expansion valve in the line somewhere, we would be able to touch both sides because that expansion valve's just in one of the tubes somewhere. They don't ever put it right up against the crash wall because it'd be too hard to get to. So if we did that again, here's my compressor. I leave my compressor, a hot, high pressure vapor. I condense into a hot, high pressure liquid. My receiver dryer makes sure that I've had time to definitely cool off a little bit, turn into a liquid. This cooling off is a relative term. So at this point, I'm somewhere around 150, 180 degrees Fahrenheit going into my thermostatic expansion valve, and because there's that restriction, my pressure drops dramatically because my compressor is trying to pull in refrigerant, and my restriction here is limiting how much refrigerant can get to it, so low pressure happens. At this point, I have a cold, low pressure liquid that absorbs heat energy in my evaporator from the passenger compartment and boils to a cold, low pressure vapor. It's sensed by my expansion valve, so I can tell whether it needs to open up more or close some more, depending on the circumstance, and then back to the beginning again. And on my fixed orifice tube system, hot, high pressure vapor, hot, high pressure liquid, cold, low pressure liquid, cold, low pressure vapor. And in this case, the accumulator sits there and makes sure that this cold, low pressure vapor, if there's any liquid in it, has a chance to relatively warm up in the engine compartment a little bit, so that it's definitely vapor by the time it re-enters my compressor. And aside from the touch feel test, the next and definitely a better judge of system operation is going to be our manifold gauge set. So we have a low side gauge and a high side gauge, and you can see the different pressures we're dealing with. Low side gauge is going to usually be somewhere in the 20 to 40 psi range. High side gauge is going to be in the 150, maybe even all the way up to 350, and that's all dependent on what the temperature is outside. Honestly, the hotter it is outside, the higher the pressure will be here, because we're not able to dump as much pressure out of our condenser, or heat out of our condenser. When we dump heat, we're also dumping some pressure at the same time. Heat and pressure go back and forth with each other all the way. If it's cold, like this time of year, we might only be seeing 150, 180 psi at the high side. The two different lines have two different color hoses: blue for low side because it's cold, red for high side because it's hot. And you can't even get these mixed up on the car, because the couplers that connect it to the system and the service ports are different sizes, so they won't even go on and if you get them up wrong. The center hose is a yellow one. It's for service, and the only time you'd ever be using that, I would be standing right next to you. So we're never going to use that unless directed to by an instructor. And these hand valves are just like if you ever turned on a garden hose before, hand valve. These are always going to stay closed, because the whole point of them is just to allow the service hose to get into one of the sides of the system. Otherwise, if we keep these valves all the way closed, you can see that there's still area around the valve here so that my gauge still reads properly. It's a pretty common misconception that you need to open the hand valves to get the gauge to work right. If you open up the hand valves, you're actually going to mess with the entire system, and so I don't recommend it. Again, safety precautions: refrigerant evaporates at low temperatures, and because of that, it can freeze your skin or eyes if contacted. It can also displace the air in a closed space or a poorly ventilated space. So whenever we're adding refrigerant or removing refrigerant from a system, we're going to make sure we have our safety glasses on, and we're going to make sure that we're paying attention to what's going on around us. Whenever we open a system, we're going to put goggles on, because if we have a malfunction with our equipment, or if you misread a situation and there's actually still refrigerant in there, we want to make sure that it has the least opportunity possible to get to your eyeballs, because that's your most sensitive spot as far as refrigerant is going to go. The rest of your body can handle it a little bit easier, but your eyeballs are very, very sensitive to that freezing. If we do get refrigerant in your eyeballs, even if you don't think that it froze your eyeballs, if you get it in the face, which it happens sometimes. Luckily, I've never had to send anybody to the hospital, but we've had a couple of issues where you start adding refrigerant to a system and you weren't working on the system before. You're just trying to get it working again. Someone who had worked on it in the past didn't get something clipped back together quite properly, and a connection blows apart. This is why we want to make sure that we're just paying attention while we're doing this stuff. So if that happens, don't rub your eyes. If you can't see or you're afraid to open your eyes, have someone escort you to one of our eye wash stations. You're going to flush your eyes for 10 to 15 minutes while I figure out what I'm going to do about the whole situation. We'll find you some first aid patches. We'll make sure that your eyes are covered, and then we'll make sure that you get to a doctor or a hospital so that they can assess your situation, and they'll probably at the very least give you an antibiotic to make sure that you don't get an infection in your eyes. And that is the end until next time. Thank you.